So we're going to use percent composition by mass in understanding a little bit more about formulas of compounds and how those are derived or experimentally understood. Before we get there, we have to realize there's two different kinds of formula. There are molecular formula and empirical formula. So molecular formula are what you're used to creating. And so molecular formula are everything that we've talked about before. We've never really talked about empirical formula. The best way I can introduce this is talking about biology a little bit. So glucose molecular formula is C6H12O6. All carbohydrates have a fixed ratio of 1 part carbon, 2 parts hydrogen, and 1 part oxygen. The empirical formula for glucose is in lowest terms, if you will. It really boils it down into not how many atoms are there, but what is that fixed ratio. And so in these ones, you've got a difference between the molecular formula, which is the actual one of glucose, C6H12O6, and you can boil that down to the fixed ratio, or in lowest terms, is the empirical formula. So there are ways of linking percent composition by mass into the empirical formula, and then the last part of this video is going to be, or this chapter is how do you go to the molecular formula from that. So sometimes the molecular formula and the empirical formula are exactly the same. So the example could be, carbon dioxide. The molecular formula for carbon dioxide is CO2, and the empirical formula for carbon dioxide is CO2. It's already in lowest terms. Water is similar that way, where it is exactly the same. Doesn't matter. The molecular formula is the empirical formula. It's already in lowest terms. A lot of organic compounds like carbohydrates and proteins and stuff like that are more often seen as a molecular formula that could be boiled down to lowest terms and being given as an empirical formula. So let's take another look at these ones. So more examples. So another relationship between them is what is that factor that they're scaled up by. So if we go from, a general carb or the empirical formula to glucose, right? You can see that it's actually 6 times greater. There is a multiplication factor that's n being an integer. So you're just basically taking that empirical formula, the lowest terms, and multiplying everything up or dividing it down. So if these are the molecular formula, if we were to put it in lowest terms, we could see that all these numbers are divisible by 2. So the molecular formula could be reduced to the empirical formula by dividing everything by 2, right? So we could have C6H5 and O2. In kind of mathy talk, you're then in lowest terms. So that's the difference. This is the empirical formula, which is a scaled down version of that molecular formula. Again, trinitrogen hexoxide, I guess you say. If we take a look at that, that is the molecular. If you were to scale that down, both are divisible by 3. And so the empirical formula would be NO2. Same one down here. We could scale this organic molecule down. So this would be the molecular formula. I don't know what this one is. To the empirical. Oh, empirical. All of those subscripts are divisible by 2, so scaling it down to its empirical formula would be C6H6NO. And that's really the only difference between these two. So we're going to carry on with calculating empirical formulas. So calculating empirical formulas starts with the percent composition. A key component in this is starting with that percent composition and assuming you have a 100-gram sample. And so that allows us to go from percent to grams when we assume a 100% sample. Or sorry, 100-gram sample. And so oftentimes in my work, I'll cross out the percent and write a gram. After we've got it in grams, we can convert from grams to the number of moles using molar mass. After that, we're going to figure out what is that ratio, the whole number ratio between the different elements. So you're going to take the number of moles you figure out and divide each one by the very smallest one in the list. Sometimes you're going to get a fairly random number, and this is because the textbook is geared towards the periodic table in the front cover of the textbook, and we're using one that has all those combining capacities and stuff on it, which is slightly different. And so it takes a little bit of approximation. So if you get a number that's like that, we're going to say the nearest whole number would be a 3. If you get a 0.5, or a 0.666 recurring or something like that, that means that you actually have to clear that decimal or clear that fraction in order to get to the nearest whole number. So always with a decimal, you could write it as a fraction, and to clear that fraction, you're going to multiply it by its denominator. So most of these ones that are done, I think there's a number in the examples here. Most of them you won't have to do them like this as you go through. So this first question says that what is the empirical formula of the following given the masses? And so we can figure out the molar mass of, the mass percent of these. And so in this, we've got this many grams of nickel and this many grams of oxygen. And so we can start with that many grams. Always start with what you know. And convert to number of moles. Now, we didn't have to do percent mass on this one. We already were given in grams. So if you're not given in grams and you are given a percent, you can go to grams by assuming a 100 gram sample. So this is all about the nickel. So the nickel was 0.2636 grams, and we want to figure out how many moles that is. Well, the molar mass of nickel off the periodic table is 58.71. And so if we do this, this gives us a number, and I'm going to write it all out, mostly for the sake of transparency here. I do find that giving about 4 digits is probably enough, and that number goes on, right? I'm going to do that same thing for the oxygen. So the oxygen tells me not percent, but just a straight up mass. And we're going to figure out how many moles that is by looking at the molar mass of oxygen. So that's the molar mass right off the periodic table. Whoops, not 16.01, 16.00. And in my calculator, this is 0.0044875, blah, 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 blah. So in these ones, they're both very, very close. Technically, what you do is take and divide them both by the smaller of the numbers. So that one by itself, and this one by the other. The numbers are very, very close. In this case, they're going to both approximate to 1. So those whole number ratios mean that that is the proportion that these elements combine in their compound. So the empirical formula for this compound that we were given information about is NiO. It's nickel oxide. And we know that because of the composition of it when we look at the mass of each of the elements that's present. So let's do a few more of these ones. So that one works out evenly. I took a big breath because I know a few of these don't, and they've got that weird fraction bit of math in them. So this one is an oxide of aluminum, and we know how many grams of each of the two components. So we don't have to go from percent composition or any of that. We can go straight to the number of moles that these masses of the different elements represent. So aluminum is off the top here, and I know that I have 4.151 grams of aluminum. I do know that each mole of aluminum, the molar mass, right off the periodic table is 26.98 grams. So on my calculator, and this is going to be a big ugly number, but I'm going to write it out for us. Something like that, 0.15, blah, blah, blah. I'm going to do the same thing for oxygen. So oxygen, it tells me that actually the amount of oxygen by mass is 3.692 grams. the number of moles that is, I've used the molar mass of oxygen. So this tells me that that's 0.23075. Always with these ones, to figure out the whole number ratio, you're going to divide by the smallest number. That one obviously is going to be 1. This one, when I divide it, on my calculator, it's 1.499 something. So that tells me it's almost 1.5, right? That's almost 1.5, or 1 1/2, if you will. Because it's a 0.5, that means that we need to multiply it all by 2 to clear the fraction. If I see this number as a fraction, that's actually 3/2. So I'm looking for the nearest whole number ratios, right? So in order to get to the nearest whole number ratio, I'm going to multiply both of these by 2. So I get a 2 and I get a 3. And this multiplying by 2 is simply to get this to a whole number value. And so the empirical formula of this, we'd have 2 parts aluminum and 3 parts oxygen. And I know that because of its composition by mass. Let's do another one. I know that this one has another fraction thing coming at us. So this information tells me that I have a compound that has vanadium and it has oxygen in it. The total mass is that. So if I want to figure out, so the vanadium is this much, right? The oxygen would be 0.6330 minus the amount of vanadium, right? This is the total of the compound. So if one part is vanadium and the other part is oxygen, that tells me that the oxygen is 0.2784 grams, just using this as my way of figuring that out. So just a little bit of extra sleuthing in this, and then we're going to do it the same. So vanadium is 0.3546 grams as it contributes to this compound. I want to figure out how many moles that is, because this mole to mole ratio, or this fixed ratio, is really important. Off the periodic table, vanadium is 50.94 grams per mole. And so that tells me, again, a big ugly number that could store in my calculator or could write it out. I'm always worried about copying errors when I do this kind of thing. So oxygen, that other part, 0.2784 grams. Figuring out how many moles it is off the periodic table. This one works out to 0.0174. Tiny, tiny numbers. I'm going to divide them both by the smallest. Obviously, this one works out to about 1. This one, when I divide it out, works out to, on my calculator, 2.49959. So what that is as a fraction, and sometimes this helps to make it a fraction, it's 2.5, right? 2 1/2, or as an improper fraction, 5 halves. If I want to clear this, if I want to make it a whole number ratio, I would multiply it by the denominator, by 2, which means I have to multiply this one by 2 as well. So this gives me my whole number ratios, 2 and 5. And so the fixed ratio here between vanadium and oxygen is 2 parts vanadium and 5 parts oxygen. And that's another example of clearing those denominators. Let's take a look at another one here. I feel like this one you could probably do on your own, but let's do it together. So we have a sample of lead arsenate in insecticide, and it has a whole bunch of different stuff in it. So it has some of lead, some component of lead, and that's 1.3813 grams. Some component of hydrogen. Oops, did I put that in the wrong place? No, I got it. Some of arsenic. And then some of oxygen. I'm just going to scroll so there's some space here. I'm going to have to copy it. You can probably still see your page, 0.42 grams. So all of these were given the mass composition already. It didn't have to go from percentage where we had to then assume 100% or 100 gram sample. So we're going to use the molar mass of each of these individual elements. So 1 mole of lead is 207.2 grams. That gives me 0.00666, big number. Same thing on all of these. We're using molar mass to figure out how many moles, because it is this fixed ratio of how many things interact. So it's a mole to mole ratio essentially, right? So 1 mole of hydrogen is 1.008 grams. That works out to 0.00666. Might notice a trend between those two. So arsenic off the periodic table using the molar mass to figure out how many moles we have in 0.49995 grams of arsenic. And then oxygen using the molar mass to convert to how many moles we have. Oh, it's a different number. So in all of these, what we want to do is divide by the smallest number. So in these, all of them, hopefully I haven't put an extra 0 in here somewhere and messed something up for somebody. So in all of these, we end up with a 1. And when I divide this one out, it's closest to a 4. There's no fraction to clear in this. So all of this work is what tells me the empirical formula for this insecticide against the potato beetle is lead, hydrogen, arsenic, and 4 oxygens. We've got a couple more examples of this, and then we've got one more topic in this chapter. So these next ones are a little bit different. And so these ones don't just give you a straight up mass, but they give you a percentage. So we've got a compound that's made up of carbon and oxygen. We've got 42.9% carbon, and the rest is oxygen. So really 100 minus the 42.9 is the oxygen percentage. And so that would be 57.1%. So these ones are different, and then we're starting with a percent composition. So what we're doing is not a lot different. So we've got this idea of what percentage each one of these is by mass, right? Remember that was mass percentage. So I start with this as a percent. And the key thing here is in order to move forward, we want this in grams like the other ones were. So if we assumed 100% sample, or sorry, 100 gram sample, I think I've said that several times incorrectly, sorry. Assume 100% grams or 100 gram sample, that allows us to go from percentage to grams. And there's nothing wrong with that. So we've just made this up into some arbitrary sample size that then allows us to go forward. So we've end up back where we were before. So we know how many grams we have. We want to figure out how many moles we have. And so using the molar mass off the periodic table, we can figure out how many moles there actually are in this compound. Same thing with the oxygen, molar mass. And this gives us very close numbers, but always we're dividing by the smallest. Close counts, but if it's really not close, then you're going to have to clear a fraction. In both of these cases, it's very, very close to 1. And so this is what allows us to come up with the empirical formula for this compound as CO, or carbon monoxide. Last one in this video and in this lesson, we've got another compound that is mostly carbon by mass and some hydrogen. And so carbon is 81.8% by mass and hydrogen is 18.2% by mass. Well, we're just going to assume 100% or 100 gram sample, which allows us to convert from percentage to grams. So I always write that in mine. assume 100-gram sample. And then we can carry on figuring out how many moles this is in the compound. So again, off the periodic table, the molar mass. Use my calculator. I get way different numbers. Going to divide each by the smallest. That one's nice. It works out to 1. This one. When I do it on my calculator, it ends up being 2.65 about. So 6.5 is a fraction. So that would be 2 2/3. It's really important to have that skill of seeing decimals as fractions. And if you do run into these ones, that's why I put that cheat sheet in your notes there, a couple pages back. So in this one, because the denominator is 3, we're going to have to multiply it by 3, which means you also have to bump this one up by 3 to get a whole number ratio. So this works out to 3, and this works out to 8. So the empirical formula for this compound is 3 parts carbon, or 3 atoms of carbon, and 8 parts, or 8 atoms of hydrogen. This is propane as a compound.